Good morning. We'll get started and we'll continue with the lecture of Professor Bhattacharya.
Continue from where we left off yesterday. So we looked at how roughly the structure of a neutron star looks like. You have a crust, you have a core, and in the crust you have nuclei, in the core you don't have nuclei, and the part of the crust also has free neutrons along with nuclei. So that's the inner crust, and then in the outer crust you have only nuclei. And in the interior you have neutron proton electron mix, which is like a fluid sea. Crust, which is roughly about 10% of the star in radius. The radius is about 10 kilometers, crust is about 1 kilometer thick. The inner part is the inner crust, and then you have NPE over here, and you have also looked at how the proton fraction changes. The proton fraction actually is minimum over here and then keeps increasing, goes at the most up to 1/8 or 12% in a pure NPE plasma. But we also saw that the energy per baryon as a function of number density of baryons, that keeps increasing as you go to higher and higher densities. And when you go to the highest densities at the core of the neutron star, then the energy per baryon becomes such that it makes it possible for other heavier particles other than just neutron, protons, electrons to spontaneously appear. So you can get heavier hadrons, hyperons. You can get matter with strange quarks, because in neutron and protons, it's only up-down quarks that are present, but strange quark is a heavier quark. So matter with strange quarks can appear as you go to higher densities. This includes both bosons like mesons, pi mesons, k mesons, and hadrons like delta, lambda, psi, sigma. At the very highest densities, you may also get to a stage where quarks get deconfined. So which means now the quarks are not bound inside hadronic structure, but you can have a pure quark C. And that could be a mixture of up, down, and strange quark as well. So what exactly is the composition at the highest densities in the neutron stars is therefore dependent very much on the details of the interaction, strong interaction at short distances, and that, as we discussed, is at the moment not a very well known, is not very well known. So therefore, there is a region which we will call inner core near the center of the star, where you will have this mixture of heavy matter, exotic matter. So you could have hyperons, then mesons, pi, k, etc., which I'll come in a moment, and then you may also have quarks. So mesons, being bosons, they will tend to form condensates. So you will end up with having either a pion condensate or kaon condensate, depending on whether the strange quarks are present or not. So the exact nature of this and at what density such new phases appear is still a matter of debate. And this is one of the things that one hopes to determine from astrophysical observations, because for any combination of these mixtures you choose, you get a different equation of state. And many of these equations of state in the table that you have seen before make different assumptions about this composition. So if we are able to constrain the equation of state, we will be able to constrain this as well. Now let's come to what is the state of matter in this neutron, proton, electron sea. As you have already seen, that this matter is fully Fermi degenerate. Now, if you have a degenerate Fermi system, it's made of fermions and mostly all states up to the Fermi energy are full, then it is a well-known fact that such a system is unstable to forming pairs of fermions if there is an attractive interaction between fermions. This is what happens in laboratory systems. If you take a piece of Fermi degenerate metal, and if the lattice provides an exchange interaction between electrons, then electrons will tend to pair, and paired electrons will behave like bosons because now you have an integral spin, and then they can form a condensate at low enough temperatures. And this is called either a superfluidity or super. The transition temperature to such a state will depend on what is the energy of interaction between these members of the pair. So you have a pair, which we will call a Cooper pair. The mechanism that provides the attractive interaction between these members of the Cooper pair, how strong it is decides what the transition temperature will be. Basically, at the transition temperature, if you come from low temperature and raise it up to the transition temperature, then all Cooper pairs are broken. If you cool it down, then the thermal energy is reduced and the Cooper pairs stay. So therefore, the transition temperature is related to the energy involved in pairing. The fermion system that we now have in neutron stars has a strong attractive interaction between these fermions. So you have a nucleon C at nuclear densities at around nuclear densities or above. So strong interaction is extremely prevalent for these particles. And for laboratory superconductors or laboratory superfluids, we know that the strength of interaction is actually quite small. It is mediated by phonons in lattice, and the interaction is quite weak. So you have to reduce the temperature to fairly low temperatures, typically to a few Kelvin, or if you have a high TC superconductor, a few hundred, it's about 100 Kelvin or so, or less, before you can get to a paired state. But strong interaction is a much, much stronger attractive interaction between particles than what you will find in a crystal. The interaction energies in this case are of the order of million electron volts. Whereas in a crystal, it is like a milli electron volt. So therefore, what do we expect the transition temperature of such a superfluid to be? And it's just, you take that interaction energy and then ask what is the temperature that will give you that kind of energy, and that will be the transition temperature. So kT of the order of the interaction energy tells you that the transition temperature of, let us say, the neutron fluid into a paired state will be something around 10 raised to the power of 10 Kelvin. This is the highest TC superconductor you will ever come across. And the thermal state of the neutron stars is such that when the neutron star is born, the interior temperatures are indeed about 10 to the power of 10 Kelvin. But very quickly, the interior cools. At interior temperatures above about 10 to the power of 8 Kelvin, there is a very strong and very fast cooling that takes place due to neutrino emission from the interior. So that will bring down the interior temperature to a few times 10 to the 8 Kelvin in a matter of days after the neutron star is born. And then the cooling becomes slow, neutrino emission becomes less dominant, then it cools by thermal conduction to the surface and then radiation from the surface. This is electromagnetic radiation. And that is a much slower process. So it takes a few million years for significant amount of energy to leave the system. So for most neutron stars that you will come across, your interior temperature will be roughly a few times 10 to the power of 8 Kelvin, which translates to a surface temperature of about a few million Kelvin. Okay? Now the rate at which this cooling occurs is also dependent on the kind of exotic matter that is present. So it's not a completely independent quantity. So if you are able to track how a neutron star is cooling as a function of time, even that will fetch you some constraints on the equation of state in the interior. And this attempt is being made, and the most recent results suggest that indeed the cooling that people have been able to measure, not the rate at which the neutron star is cooling, but you take neutron stars of well-determined ages. That will happen if you have an associated supernova remnant, for example. So you can measure the age of the supernova remnant. The neutron star's age will be known. And then look at the surface temperature and collect a sample of these. And then you see how, as a function of age, the surface temperature of the neutron star is changing. And that tells you the rate at which the neutron star is beginning to cool. And most recent estimates suggest that indeed there appears to be some evidence of there being some exotic matter like ion condensate or some strange matter in the interior.
Doesn't this depend on the mass of the neutron star?
No, so there will be a band, mass of the neutron star. Typically, when you are looking at neutron stars born initially from the supernova explosion, those masses are not very different. They will cluster around 1.5 solar mass. The heavier neutron stars are typically mostly seen in systems which have accreted mass and then have grown to much larger masses. So binaries give you heavier neutron stars. I mean, all neutron star masses we measure are in binaries, otherwise we cannot measure masses. But we can tell in cases where the neutron star would have undergone accretion, and those cases where they may not have undergone accretion. And the latter typically has masses ranging from about 1.2 to about 1.5 times the mass of the sun. And so yes, there is a mass dependence. In fact, the interior composition also is mass dependent. So even if you have the exotic matter at the center, the amount of it will depend on the mass of the neutron star, because a different mass gives you a different central density. A higher central density will give you a greater chance of creating these exotic matter. So yes, the cooling is mass dependent, but for a typical mass of a neutron star, you can compute a cooling track. And the recent estimates, as I said, the claim is that even taking into account all these variations that are possible, even putting in the effect of magnetic field on cooling, it is not possible to explain the rate at which the cooling is being seen unless there is some exotic matter at the center. So anyway, so that's one of the ways to get constraints on the nuclear equation of state. So cooling is something that is not been very constraining until now, but it's more recent observations are beginning to provide interesting constraints. So all right. So coming back to this. So clearly, very quickly after the formation of the neutron star, the interior temperature is going to fall below the transition temperature of the superfluid here. So you expect the neutrons to pair up and form a superfluid state. Now the superfluid pairing can be in different types of states. A typical Cooper pair in regular superconductor like lead or something that we'll talk about. That's two electrons pairing with opposite spin and mediated by a lattice interaction. So that kind of pairing is called a S-waves pairing. But in principle, you can also have pairing with angular momentum. You can have two fermions, they pair and also they have a rotation around each other. So the first order of that kind of rotating system we'll call a P-wave pairing. And there are different transition temperatures for these different things, and the amount of energy that you gain by doing pairing of different kind also depends on the density of this material. So people have looked at this, and then the verdict is that the neutrons in the core form a P-wave superfluid. In this region. But recall that there are also free neutrons in the inner crust. And the temperature is below the transition temperature for them too. So even these neutrons are going to be superfluid, except at these lower densities, it appears that the S-wave pairing wins out. So you have S-wave superfluid over here. This whole region then has neutron superfluid, except the pairing mechanism is somewhat different in the core compared to. What about protons? If neutrons can pair, protons can too. Will there be any difference? Exactly the same numbers should apply to protons, because as far as strong interaction is concerned, protons and neutrons are identical. There is no difference. The strong interaction does not see a difference. This is isospin invariant. So what neutrons can do, protons will do as well as far as strong interaction is concerned. Only difference is the proton number density is much smaller than the neutron number density. So pairing will occur, except at those number densities, the gap energy or the energy of interaction between protons is a little lower, because average interproton distance is larger compared to average interneutron distance. So if you look at the strong interaction potential at a larger average distance, the interaction potential is lower. So you will have again a paired state, but with a somewhat lower, maybe an order of magnitude or a little more, lower than the neutron transition temperature. Nevertheless, that transition temperature is still above the interior temperature that you will have in most neutron stars. So the onset of proton pairing may be a little delayed compared to onset of neutron pairing, but when you're looking at any typical neutron star in the sky, you expect even the protons to be in a paired state. So you will have, so this is a charged fluid. When they pair, they will form a superconductor. That is in this region. In the inner crust, of course, there are no free protons. All protons are bound in nuclei, so there is no question of there being a proton superconductor in the inner crust. Now you can see we are dealing with a system where we have two quantum fluids occupying the same volume, mixture of two different quantum fluids occupying the same volume. They have different properties. One is a superconductor, one is a superfluid. How about the electrons? Both neutrons and protons are paired, and the form is formed a coupled condensate. Do you think the electrons will do that as well? That is correct. So you need to have an attractive interaction between electrons which will overcome their Coulomb repulsion, and there is actually no mechanism that is going to provide any attractive interaction of a magnitude which can lead to pairing at temperatures as high as 100 million Kelvin. Right? So electrons are not paired. Electrons are normal. So this is like a normal electron Fermi degenerate gas which is present over there. So this is you can see the complexity of the system now. So you see that you have a quantum fluid of neutrons, quantum fluid of protons, and a normal electron gas, all coexisting in the same space. So this allows for some really rich phenomenology of interactions. To understand that, let's now start getting into other properties of this neutron star. So the neutron star, when it's born with a significant amount of spin. So neutron stars rotate, and we know this from pulsars. You can see pulsars rotating as fast as 1.4 millisecond to there are pulsars in binary systems, accreting binary systems, where spins can go up to hundreds of seconds. So it's a range of spin, but it's still pretty fast spin. Another thing the neutron stars have, which are also observed, is a strong magnetic field. The average magnetic field of a neutron star is about a teragauss at the surface, 10 to the power of 12 Gauss at the surface. And then there are neutron stars which have even much stronger magnetic field, going to a few times 10 to the power of 15 Gauss. We tend to call them magnetas. And the lowest magnetic fields in the neutron star that have been measured are about 10 to the power of 8 Gauss. So even that is a very strong magnetic field compared to what we can do, what we can find on Earth. So neutron stars again harbor the strongest magnetic fields we know in the universe. So these, of course, are carried by the material which is present in the neutron star. So let's look at these two aspects of how does the neutron star structure carry these different attributes. If this was a complete rigid body, then of course there's no question as to how the rotation is carried. The whole neutron star is rotating rigidly. Everything is coupled to each other. The rotation in a system that we now have, where we have a crust, solid crust, and we have a large part of the matter in the interior being superfluid. So as we know, a superfluid cannot have bulk rotation. Not possible. It's a pure quantum state. So if you take a closed path the whole state is described by a single wave function. If you take a closed path and integrate, your theta must come to the phase must be integral multiple of 2 pi, and therefore that tells you that you really cannot sustain a rotating velocity field in a superfluid. So how does a superfluid carry rotation? Do people know about this? A laboratory superfluid, for example, if I rotate it. So initially, if I put a superfluid in a container, I rotate the container outside, the container will keep rotating, it will slip. The superfluid will remain stationary. But over time, some amount of angular momentum can be transferred to the superfluid. And when the angular momentum gets transferred to the superfluid, how does the superfluid manage to rotate? That is correct. So, rotation in the superfluid neutrons is carried by these are called Feynman-Onsager vortices. So, these are vortices, quantized vortices. So, the vortices have this following structure. You have a core in which the matter is normal, it is not superfluid. So this can rotate happily without any problem. And then you have a 1/r superfluid velocity field around it. So you have a circulation around the normal core. The vorticity carried by each quantized vortex is kappa, can be given as h divided by 2 times the mass of a neutron. That's because a pair has 2 neutrons, is really the mass of the pair. So now, each vortex carries a certain amount of vorticity. The whole star has some large amount of vorticity, so that will get split up into individual vortices, and the number of vortices will depend on the total angular momentum of the star. For a spin period of 1 second, you expect about 10 raised to the power of 16 such vortices in the interior. N vortex is of the order of 10 to the power of 16 p to the minus 1. Rotation of the neutron star is not constant over time. As I said, the neutron star also has a strong magnetic field. And this magnetic field, of course, is seen outside, and you have a magnet. If you rotate a magnet, then it is going to produce some electromagnetic radiation. The lowest order is going to produce magnetic dipole radiation, and that radiation is going to carry away energy at the expense of the rotational energy of the neutron star. So this rotation is going to slow down with time. The neutron star spins down, and every pulsar we know, if we look at its spin history, you can measure it's steadily spinning down. So that means the electromagnetic force, the electromagnetic torque that is applied on the neutron star makes it spin down. Electromagnetic torque is applied on the crust because that is the place where the magnetic field is anchored, the external magnetic field is anchored. So the crust is spinning down. Will the superfluid feel this change? How is this information going to be transmitted to the superfluid? As I said, you have a container, you rotate it, it's not going to immediately transfer this. And in an ideal condition, it will never transfer this information to the superfluid. So how is the superfluid going to know that the neutron star is experiencing an external torque and hence it is spinning down? Okay, so you are saying that this is going to happen only in individual episodes because quakes cannot be continuous, right? That's part of it, but there's more to that story. In fact, most of the neutron star, the entire core superfluid, is so strongly coupled to the crust that it almost spins down simultaneously. How can that happen? That has to do with the property of this vortex. When you have POF pairing, you have two neutrons, they are actually spin parallel and going around each other in an orbit. This system has a magnetic moment, because neutrons have magnetic moment. So these vortices actually have an intrinsic magnetic moment. So much so that the magnetic field due to that POF pairing near this vortex core could be as high as 10 to the power of 13 Gauss. That's part one. Part two is that this neutron superfluid coexists with a proton fluid. It's a proton superfluid. Strong interaction does not distinguish between protons and neutrons. So I said there is a superfluid circulation around the vortex. That is dragging neutrons around. The neutrons are going to drag their fellow protons around as well. So this proton circulation around the vortex core creates a current, and that creates a magnetic field. And this magnetic field is even stronger. Near the core, this magnetic field could be of the order of 10 to the power of 15 Gauss. So these vortices are not simply rotating discontinuities in the neutron superfluid. They have a very strong magnetic field associated with themselves. Now, consider the crust spinning down. There are free electrons in the crust. There are free electrons all over this place. Electrons can move all through the neutron star. Crust is spinning down. Electrons will carry that message. They will go through the interior as well. And now that these vortices have an extremely strong magnetic field, this is due to P-wave pairing and proton drag. Together gives you magnetic field of the order of 10 to the power of 15 Gauss around the vortex. So once an electron encounters this magnetic field, it is going to scatter on the magnetic field and transfer momentum. So vortices will feel the spin down in the crust. So how does a superfluid adjust to such forces? So if you have vortices located at some places, and the superfluid is moving around, which is basically sum of the velocity field of all the vortices together. If the vortices now feel this external coupling because of the electron motion, they are going to follow the crustal rotation. So the superfluid has a rotation speed which is simply decided by the density of vortices. If the density of vortices have not changed, then there is going to be a relative circulation velocity between the vortices and the background superfluid. In that condition, the vortices will feel what's called a Magnus force. If you have a vortex which is traveling with respect to the background fluid, then there is a force that gets generated at right angles to this motion. So that Magnus force will be outwards, and it will tend to push the vortices outwards, resulting in a reduction in the space density, surface density of these vortices. At the boundary of the neutron star, the vortices, if they come and hit the boundary, they will annihilate. So you will get a reduction in the number of vortices and the vortex density reducing. And that is exactly what happens when its superfluid spins down, because the angular velocity of the superfluid is simply given by, is a proportional to the number density of vortex. So the superfluid is going to therefore spin down, core superfluid is going to spin down because of this strong interaction, magnetic interaction between the itinerant electrons, which are normal all over the place, and the magnetic fields associated with the vortices. Now let's look at this little region where you have neutron superfluid. It is a S-wave paired superfluid, and there are no free protons. So they also have vortices, but these vortices don't have magnetic field. So this mechanism, which is coupling the bulk of the neutron star, which is the core, with the crust, actually does not work for the crustal superfluid. So the crustal superfluid is therefore more loosely coupled. And how is it coupled at all? The crust is something else. This is neutron drip region. The free neutrons in there have formed the superfluid and they have vortex. But there are also nuclei present, right? So it is not a homogeneous medium. At every little distance, you have a nucleus. These vortices can pin to nuclei. That means if the core of the vortex overlaps with the nucleus, then the net energy is reduced. So you have a tendency of the crustal superfluid vortices to pin to nuclei. Okay? So core superfluid has a strong coupling with crust. But crustal superfluid here we have vortices into nuclei. Nuclei are rotating along with the crust. So a similar situation then operates, that the vortices, because they are pinned to nuclei, they now rotate at a rate determined by the crust. But the background superfluid is rotating at a rate determined only by the number density of these vortices. So as the crust slows down, the rate of motion of these vortices reduce. So the vortices are now going around more slowly, but until the vortex density has been reduced, the superfluid continues to rotate at the old speed. So now again there is a relative speed, there is a Magnus force, which will tend to push the vortices outwards. Outward migration of vortices. But this may not happen instantly, because as I said, vortices are pinned, and it will take some minimum amount of energy or some amount of force to yank them off the pinning and then making them move. So the Magnus force has to build up. The magnitude of the Magnus force has to build up to an extent that the vortex can be yanked off a pinning site. Once you have reached that, then the vortex will unpin and will try to move. And it will migrate and then find a new pinning site. No, so because they're pinned, even to dislodge them, you need some amount of energy, right? If your force is less than the pinning force, or energy is less than the pinning energy, then the vortices are not moving at all. They're just stuck, right? The edge effect is a different matter altogether. So if the vortices go to the edge, they will of course annihilate, and then the total number of vortices will gradually go down with time anyway, because that's how the total angular momentum of the superfluid is decreasing. Which is going to happen, that is similar to what is going to happen to core vortices too. But what is happening here is that you have a pinning site. Unless the force builds up to more than the pinning force, the vortices don't move. So the angular velocity difference between the crust and the superfluid keeps building up. Magnus force is proportional to the velocity difference, angular velocity difference. So the omega minus omega s, omega s minus omega is a superfluid, minus omega is going to build up. Until unpinning. So this is going to cause a jerky adjustment of the superfluid angular velocity. Omega minus omega s will build up. Omega sf is constant, omega is going down. So this is going to build up, and when the Magnus force becomes strong enough, then the vortices will unpin. Let go. As soon as vortices unpin, because of the Magnus force, they're going to move out. If they move out, then the number density of vortices go down, which means the superfluid angular velocity goes down, which means the superfluid angular momentum goes down. Where does this angular momentum go? It goes back to the crust, right? So what you will see is that suddenly, when this collective unpinning happens in a certain region of the crust, you have certain amount of angular momentum suddenly given to the crust. So if you look at the spin rate of the star from outside, you'll see that the spin frequency as a function of time was declining due to the external torque. What we see is only the spin frequency of the crust, by the way, because we are only watching from the outside. We don't know what's happening inside. And at some point, suddenly some angular momentum is deposited in the crust, excess angular momentum deposited in the crust. So you get an increase in omega. Interestingly, what you will then also see accompanying, if you look at omega dot, for this short period, I'm going to say that omega dot was at some average value. Omega dot also decreases with time, by the way, but maybe I should not draw it this way. Omega dot is negative. Okay, I'm taking the magnitude of omega dot, decreases with time, and then a huge increase in omega dot at the same time as this. And over time, you will see this. It may take many months. This excess omega dot will slowly decay away over time. What is this telling us? We have an external torque determined just by the magnetic field. So as far as the external world is concerned, the torque really hasn't changed very much, at least over this time. So what can cause omega dot of the star, as we see from outside, to go up? The star has an omega dot because an external electromagnetic torque is applied to the star. Right? It has angular momentum, which is I omega, and d dt of I omega is the external torque. I is the moment of inertia. Right? So you have external torque N is I times omega dot. So N has more or less remained the same over this short time. So, and omega dot has increased. What does that mean? I has decreased. So I decreases and then increases back again slowly. How can this happen? Can you imagine a situation where there is a well-defined structure like a neutron star? Its moment of inertia suddenly decreased and then gradually increased back over time. This is a telltale signature of superfluidity in the interior. What happened here is now the crustal superfluid is not pinned anymore. So crustal superfluid has no coupling anymore to the external torque. So crustal superfluid is doing its own thing, whatever angular velocity it acquired. It is not feeling the torque that the crust is receiving. So that means that bit of the moment of inertia is not coupled to the external torque, because it's not feeling the torque. Over time, gradually, these vortices will find new places where they can pin in nuclei. Gradually, more and more vortices will get pinned. All the vortices that moved eventually will find new pinning sites and get fully pinned. And then the full moment of inertia will get recoupled. And only if the interior is superfluid can you have long time scales like months for this to take place. If it was any other type of material which did not have superfluid property, then this would happen very, very quickly, in seconds. So the superfluidity plays a role in many things. It plays a role in the cooling rate. It plays a role in viscosity. It plays a role in multiple different properties of the neutron star. Coming to the magnetic field, we said that the neutron star has very strong magnetic fields, right? Teragauss on an average. How is this magnetic field generated? What is the source of this magnetic field? Sorry? Yes, that is likely the case. Right after neutron stars were first discovered, a suggestion that was made, and it was quite popular for a while, and that is, you take the neutrons. Every neutron has a magnetic moment. You align them all up. Let's say all neutron magnetic moments in the neutron star is aligned. Then how much magnetic field will you get? You'll try to do that in the tutorial session today. But you can get a very substantial magnetic field that way. But later on, the more detailed exploration has shown that you really don't have a mechanism to get all neutrons to align. In fact, if the neutrons do not align and are randomly oriented in their magnetic moments, then that is in fact a lower energy state than having a ferromagnetic state with all neutrons aligned. And there is no external agent which will allow to have a phase transition from a disordered neutron state to a fully ferromagnetic neutron state. So that idea was soon given up as the origin of neutron star magnetic fields. And it also does not sit well with many observations of the fact that, for example, the magnetic fields can have such a large range, from 10 to the 8 to 10 to the 16 Gauss. It's a factor of 100 million. So if you have this kind of ordered state, you really cannot accommodate such a large range of magnetic fields. And then you do have magnetic fields that change with time. If you have a ferromagnetic state, you cannot have gradual change of magnetic field with time. So what we understand is that the neutron star magnetic fields are actually generated by charge currents. The charge currents could be electron currents in the interior, and in the core, you would have electron currents, but since the protons there form a superconductor, the magnetic field has to be carried just like neutron vortices. Here the magnetic fields will be carried by Abrikosov fluxoids. So proton superconductor, magnetic field is carried in Abrikosov fluxoids. Which have a structure like this. They have a normal core through which the magnetic field passes. And around the normal core, there is an exponential screening of the magnetic field. So this is the typical length. Screening length is called the London length. And the core size is called the coherence length, psi. So this kind of structure is only possible as long as Xi is significantly less than lambda L. In fact, the condition is that lambda L by Xi must be larger than square root of 2. Only then fluxoid structure like this is possible. They're called type 2 superconductors. And it so happens, if you look at the parameters of the proton superconductor, it happens to be type 2. So it will be able to carry magnetic fields like this. So these are structures similar to vortices in the sense that they are topological similarities in the quantum fluid. But the proton superfluid also rotates. Should the proton superfluid have vortices in it to rotate? It's a charged superfluid. The proton superfluid does not need to have vortices to rotate. If you have a charge, then the momentum that we use for the pair, in case of neutrons, it will be just P. In case of protons, it will be P minus charge times the vector potential divided by C. So the discontinuity that you need in P to carry rotation is not required because now you have a vector potential which compensates for it. So all it will do is it will create a surface, very small surface current around the whole superconductor, which will be enough to carry the, to satisfy the condition for the superfluid to rigidly rotate. So superconductor will rotate like any normal fluid, except for magnetic field, it will have to create structures like this. So you have these two types of discontinuities floating around in the same space. You have neutron vortices, you have proton fluxoids. You can estimate how many fluxoids you will need from the fact that each fluxoid carries a flux quantum, which is hc by 2e. If you look at the total magnetic flux, you can divide by this number, you can find the number of fluxoids. So it will be a very large number. So the core superfluid, in addition to these electron scattering communication with the crust, will also find additional inhomogeneities to into, which are these fluxoids. And this is proton superfluid is actually co-rotating with the crust. So these fluxoids are going to co-rotate with the crust. And in addition to the electron scattering communication that I talked about, you also have this. These proton fluxoids actually have 10 to the power 15 Gauss magnetic field going through the core. They are fluxoids after all, carrying the magnetic flux. And you have these magnetic fluxoids and magnetic vortices, they are going to interact with each other. And so momentum transfer can happen also through this mechanism. No, it's just 1 over r. It's, the scale here is xi. Xi neutron, call it. So this is 1 over r over xi is the scale. There is a coherence length for every quantum fluid. So that is the distance over which the property of the fluid will remain correlated. And that will be different for, it depends on the gap energy, it depends on the number density. So therefore, it will be different for the neutron superfluid and the proton superfluid. And I will call this Xi, and this is London length. London length is simply to do with the electrical screening. So, So if, first of all, if it is a type 1 superconductor, then we will expel magnetic fields. If it is a type 2 superconductor with magnetic field strength below the first critical field, then it will have Maxwell effect. If the magnetic field is between the first critical field and the second critical field, then it will carry field in vortices. And above second critical field, it will destroy the superconductivity altogether. Right? So there are all these different possibilities. Neutron star interior is a even more complex entity. And that's because there are electrons present. Electrons are normal. Electrons are going to carry the magnetic field no matter what you do. If you have to expel the magnetic field from the interior, you have to expel all the electrons. Certainly there is no energy source for doing that. So it is a given that the magnetic field is going to penetrate the interior and run. So how does the proton superconductor carry this magnetic field? It has to go through the superconductor as well. So the superconductor has to produce these fluxoids to carry the magnetic field. So the overall magnetic field in a typical neutron star could be even somewhat less than the first critical field of the proton superconductor. But nonetheless, it is going to make vortices and carry those fields because of the presence of electrons. Any other questions? Yeah, so these are, these cores are not superconductor. The circulation around it is of superconducting fluid. Right? So cores have size of the order of the coherence length, which is of the order of a Fermi. Normal matter in this core, which is a few Fermi across. Because the vortices are carrying the overall angular momentum, right? So they will eventually all have that same sense, except the vortices need not be just straight and parallel. They can have twists and turns, but there will be overall sense given by the net angle. Now let's move to something a little different. So we have looked at the way a neutron star is made. We have looked at the major components of the interior. We have known that the neutron star has strong magnetic field and it has got a rotation. And we also know in most of these neutron stars that we see, we see them as pulsars, which means you see a radiation beam pointed towards us and it goes around, and every spin period you see a pulse because the beam is pointing towards us. And this external radiation beam is connected to the magnetic field. It's around the magnetic pole. So such a radiation of pulses, as we see it, is only possible if the magnetic field axis and the rotation axis are not aligned. If both were aligned and the beams were going only around the spin axis, then you actually will not see this pulsating signal function of period. So in general, for neutron stars, the spin axis and the magnetic axis are not aligned. And assume there is a strong magnetic field in the interior. The magnetic field in general will produce an anisotropic pressure. In addition to the pressure of the material that we have got already from the equation of state, the magnetic field also is going to add to the pressure. And this pressure is going to be anisotropic because magnetic field has an axis. So if you take this pressure into account, then you can have a little deformation of the neutron star, which will be symmetric around the magnetic axis. And this deformation now being, so let's look at magnetic deformation. So this is the star. This is the magnetic axis. then in an exaggerated fashion, I can consider, okay, this is only polaral magnetic field, then I can consider a deformed star like that. And let's say it is spinning around an axis over there. So of course, this neutron star is going to produce electromagnetic radiation and it's going to spin down because of that. But this deformation can be viewed as there being an ellipticity of the neutron star, which is not aligned with the rotation axis. And any ellipticity which is not aligned with the rotation axis is also going to produce gravitational radiation. Well, this is a fact. We know that in almost every neutron star we observe. Why is a question of how the magnetic field was generated in the first place, right? And that is a more complex question. I don't think there is a definitive answer to that. There are many scenarios which we can talk about where you will generate a magnetic field which is in arbitrary orientation, in fact, with respect to the spin. I think the spin doesn't matter, right? If the processes that generate the magnetic field have no influence from spin, then you would expect an arbitrary orientation between the two axes. And by and large, that appears to be the case. The mechanism that give rise to the magnetic fields in neutron stars don't seem to be related to the rotation itself. So we can talk about what those mechanisms are. I'm not planning to cover that in these lectures because that's a whole subject in itself.
Good morning, sir. I wanted to ask about the vortices you explained earlier. You said that the matter core of that vortices are made of matter, not superfluid. How they are made up? What is the process of their formation? I mean, there is superfluid all around the neutron star core. So how normal matter is there in that core? And also,
it is the same neutron matter. The pairing breaks. So the neutron matter which is inside the superfluid core, they do not have Cooper pairs anymore because now the rotational energy per neutron is so high in that core that that energy is larger than the pairing energy. So therefore the Cooper pairs break. It's nothing different from the matter that you see elsewhere, except that the pairing is no longer.
Okay.
Does that answer your question?
Yeah. Also, I wanted to ask about the pinning of the nuclei in to the magnetic field. Can you explain more on it?
Pinning of the vortices to nuclei, right?
Yeah.
So neutron superfluids in the crust have also these vortices. And these vortices have a core which is normal. And this normal matter occupies a region which is of a few Fermi, which is a typical size of a nucleus. Now it so happens if some part of this core overlaps with a nucleus inside the same region, then the net energy required, remember you need some energy to create normal state from the superfluid state. If some part of that state is already occupied by pre-existing normal matter, the net energy required to create that vortex goes down. So therefore there is an energy gain when a nucleus sits inside the superfluid vortex core, right? And because there is an energy gain, there is a force. If you move the vortex closer to a nucleus, the energy goes down. So therefore, the gradient of this energy is equivalent to a force. So that is the force. So it doesn't mean that the nuclei will have to exactly overlap with nuclei in every place, the cores, but just the fact that there are many vortices, many nuclei, and vortex may be close to some of them, will result in a force with which it is attracted to nuclei. And that's what we call pinning.
Thank you, sir. Also, I had one small doubt. There was formula for NV, not exactly the formula. The value for NV approximately is 10 to the power 16, and there was P inverse. Can you tell me what is P here?
Oh, okay. So this is spin period.
Okay. Thank you so much.
Spin period in seconds. All right. Any other question? Open go to the rotation axis. No, I'm saying that the rotational deformation here is, it could be small, but even if it is there, any deformation which is perpendicular to the rotation, is symmetric around the rotation axis, will not lead to any gravitational wave emission. Right? The only thing that matters is something that is misaligned to the rotation axis. So we are specifically dealing with the cases for gravitation. Yes. So if you have a fast rotating neutron star, of course, it will become oblate because of rotation itself. I'm not dealing with that now. I'm dealing with over and above what the magnetic field is contributing. That is in the neutrons, no? Not in the proton. So protons do not require Feynman Onsager vortices. But in any case, the vortices, fluxoids that you're talking about, they are the consequence of angular momentum and magnetic field already having been inherited from the pre-neutron star state. Right? You realize that the superconductivity sets in well after the neutron star has formed. Superfluidity sets in also after the neutron star has formed. So whatever magnetic field and rotation was there was already there from before superfluidity and superconductivity came into being. Okay. So how does it form at the temperature?
A low enough temperature to form a.
Yes, so what is low enough temperature? That's what I explained in the beginning. The transition temperature depends on the interaction between neutrons in this case. And neutrons are very close at distances of Fermi, and the strong interaction at that distance has energy scale which is in many millions of electron volts. So therefore, the transition temperature is 10 to the power of 10 Kelvin or more, and the interior temperatures are lower than that. So it is well below the transition temperature because the transition temperature here is very high, because the interaction is mediated by strong interaction, unlike laboratory solids. What happens within the inner core depends very much on what is present in that core. If, for example, they are pi mesons and k mesons, then they are not fermions. You are not even talking about any superfluid superconducting state, but you can have a condensate. You can have a Bose condensate. If you have quarks, particularly some certain proportion of quarks in different colors, then you can have a color flavor locked superconducting state, CFL state, as they call it. Right? So it is all possible. But I don't want to discuss that because things are somewhat uncertain. So there are many different possibilities that exist for the core. It depends on the composition. Okay, so let me, having done this, let me just quickly write down an expression and then we'll close today. So how much is the magnetic deformation that we expect? So the ellipticity for a given magnetic field and a ratio called lambda, I'll tell you what that ratio is roughly equal to 10 to the power minus 5 times 1 minus 0.4 by lambda. But the lambda is it's the total amount of energy in the poloidal component as opposed to the net total energy. Now, if you have a pure dipole field, lambda is 1. Everything is in poloidal component. But there is no guarantee that the magnetic fields in the inside of the star is purely poloidal. You can also have a strong toroidal component. If you have fully toroidal component, then B poloidal is 0, lambda is 0. So if lambda is 1, then you can see that you have about 60% of this number have ellipticity of the order of 10 to the power minus 5 if the internal fields are strong, 5 times 10 to the power 14 Gauss. If you take a typical field of 10 to the power 12 Gauss, then this will be 2 orders of magnitude lower. And the amount of gravitational wave that we expect to receive from this is h. This is the gravitational wave amplitude, is roughly 4 times 10 to the power minus 30, 1 by distance in kiloparsec, period in second, or let me not write period. I'll write this as frequency. Frequency of the gravitational waves squared. Neutron star moment of inertia in units of 10 to the power 45 grams per gram centimeter squared, and epsilon in unit of 10 to the power minus 6. Main expression is h naught is 4 pi squared gi over c to the power of 4. So if you put in the numbers, you'll get this. So you can see that if epsilon minus 6 is of the order of 10, the frequency of the gravitational wave is twice the spin rate. Right? So you'll have twice. So if you have 1 second, then frequency of the gravitational wave is 2 hertz if you have a 1 second rotation period, and this will give you 4. So it's for a typical pulsar, this is small value of the order of 1. If you take a millisecond pulsar, then this will become larger by a factor of 1,000. You can have a factor of 1,000,000, but in a millisecond pulsar, the magnetic field is much lower. What we find is all these low magnetic field neutron stars like 10 to the power 8 Gauss are the ones which end up as millisecond pulsars. The reason for that we will discuss tomorrow from binary evolution. But so you may gain in this, but you will lose in epsilon. See that epsilon is directly proportional to the magnetic field. So if you take 10 to the power 8 Gauss, then you will get about 1,000,000 times less in epsilon. You will gain a factor of 1,000,000 in f squared, you will lose a factor of 1,000,000 in epsilon. So it really doesn't change very much in terms of the total amount of gravitational amplitude that you will get. But this is a steady source of gravitational wave at a well-known frequency once you know the pulsar. So if you keep accumulating data for a very long time, then it may be possible to bring this signal out of noise. So this is one of the possible sources of continuous gravitational waves that will. So tomorrow we will also talk about other important contributors of continuous gravitational waves from neutron stars, like R mode oscillations. Since we are out of time, we'll stop here now.